than that, there is a potential function in the class of original condition. Now, when we have an equilibrium solution, we have a pure strategy or mixed strategy. This solution, this profile combination of strategies for the agents is stable in the sense that no one has an incentive to deviate, given that the others play with the play. But everyone optimizes their own utility function in the game. So if, as a system designer, we have some other objective that we would like the system to have, for instance, social welfare, the sum of utilities for all the players, or the maximal time of completion of the task, like make spells, something else, and we may have different objectives. So those may not necessarily optimized by a Nash equilibrium. Right? So a Nash equilibrium does not have to be an optimal solution given some objective that we as a central planner may have. And so the question is, if we let the system to converge to a Nash equilibrium, how bad can it be? Okay. So how far is a Nash equilibrium solution from an optimal solution in the system? Now the question was asked first in the context of congestion games. There was a paper named How Bad is Selfish Routing. But the measure of efficiency of equilibria that we will talk about today actually applies to all games in normal form. And in fact, the essence of that measure is just an approximation ratio. And so we have some optimal solution, we have some other feasible solution, and we just take the ratio of the value given by the optimal solution and the feasible solution. So basically, this is just an approximation ratio that the Nash equilibrium uses. But let's get to this now. So Nash equilibria may be suboptimal, and in case of congestion games, this is one of the famous examples. It's called Figures example. Here we have a very simple network. There are only two links, parallel links from one node to another node, and the cost function on the upper link equals the congestion on that link. So every user of that link will pay X if there are X users on that link, and the lower link has a constant cost function M, which is the total number of players in the game, and it does not depend on the actual congestion, right, on that link. Now, what would the network users do, the selfish, interested ones? What would you do? Which link would you take?
The lower one.
The lower one. Why?
Lower cost to me.
Well, X is the congestion, the actual congestion in the upper link, and is the total number of players. So X cannot be ever higher than N. Why wouldn't you hope that X will be actually strictly lower than N and take the upper link?
Depends what portion of the cost is on me.
Yeah, but in the worst case, all of you are there and you still pay N no greater than that. If you take the lower link, then you sort of convict yourself to play N, and that's not minimizing your cost. Right? So that's actually quite the opposite of minimizing the cost. You're maximizing the cost. Right? So if you take the upper link, you never pay more than on the lower link. Right? So it's better for you, it's a dominant strategy in this case, to take the upper link. So all the users will take the upper link, or say there are actually two equilibria here. What? Sorry.
I didn't mean the lower in height. I meant the lower in cost.
The lower in cost. Well, I was asking for which one is the lower in cost. Okay. Right. So there would be two stable solutions here. Either everyone takes the upper link and no one the lower link, everyone has the cost of n, okay? Or in fact, we may have n minus 1 agents up and just one agent on the lower link, but still no one has incentive to deviate, because in case of deviation, the cost that they will pay will be exactly n. Okay. So there are two very similar Nash equilibria here. Is that an optimal thing to do? Would you, as a central planner, divide the agents of the network so that the total cost that they all pay would be lower than what they pay in the Nash equilibrium? So what do they pay now in the Nash equilibrium? I'd assume that all of them take the upper link, everyone pays the cost of n. There are n of them, so n squared is the total cost in the network. Can you reduce it? Can you force the agents to divide themselves differently and reduce the cost? Yeah, how?
So if you put half each way, then half of them would pay n, but the other half would pay half of that. So on average,
Yeah.
3/4 n, I guess.
Yeah, so at least half, you can put half of the agents on the lower link, each of them will pay the same cost n, but the other half will be the lucky ones, right? They will pay only n over 2 now, right? So in total, you will reduce the cost by indeed 3/4. So there is a difference between the value of the optimal solution and the equilibrium solution. And we would measure the efficiency of equilibrium with what is called the price of anarchy or the price of stability. These are two approximation ratios. One is for worst possible Nash equilibrium, the other one is for best possible Nash equilibrium, in terms of our objective function. So the objective function can be different. We may like to minimize the total cost or maximize the total utility in the system, or we would like to minimize or maximize, minimize the maximum load or delay of completion of the task, make span, and so on. So there may be different objectives that the designer may have. So then, if we have this optimization goal, we define the values of the optimal solution and every other solution, the equilibrium solution, and we take the ratio. Okay. So the price of anarchy would be take the value of worst equilibrium divided by the value of the optimal solution, and for the price of stability, we will take the value of the best possible equilibrium and divide it by the value of the optimal solution. Now this definition, this direction in the ratio is for a maximization problem. For a minimization problem, and then the value of the equilibrium will be always no less than the value of the optimal solution, so the ratio is always greater equal than 1. Right? So if we have a maximization problem, then we have to inverse the ratio so that we divide the value of the optimal solution by the value of the equilibrium, so that always the ratio is greater or equal than 1. Okay, so that's the definition. Let's count the price of anarchy and stability in some games that we know. Prisoner's Dilemma. We remember that in this game, the Nash equilibrium was so not good for both of the players. So if we want to maximize the total utility in the game, then we would advise the agents to play deny instead of confess, which is the unique Nash equilibrium in this game. Right, so the value of the equilibrium is 2 here with those pair functions. The value of the optimal solution is 20. So we divide 20 by 2, we have the price of anarchy and the price of stability equal 10 because we have the unique Nash equilibrium. Right, so it's also the best and also the worst. questions? Battle of Sexes, another game that we know. There are two Nash equilibria here, and they have different values in the sense of the total utility. Right? Theater has the value of 3. Football has the value of 4. So the first one is the worst equilibrium, the second one is the best equilibrium. And also, the best equilibrium in this case is the optimal solution, right? So the price of stability must be then 1, right? The best equilibrium gets the value of the optimal solution, so the ratio is 1. But the price of anarchy is 4 divided by 3, 4/4. There are some general results about how bad the price of anarchy or stability can be in games. There are really lots of results for different forms of utility functions and game contexts. I will only talk about the simplest one, and they were actually the first results that we achieved in this direction. If we have a congestion game, to remind you once again, that's the game where we have a set of agents sharing the set of resources, and for each resource, its cost to utility function depends on the congestion of that resource, and this is what each one of the users of that resource would pay, right? And then the utility cost of an agent is the linear sum of those cost to utilities across the resources that that agent uses. Right? So if we have such a game and the resource cost function is of linear form, so that's some coefficient AR multiplied by K, which is the congestion on the resource, plus VR, another constant, and each agent wants to minimize his cost, which is the sum of the cost across the resources he uses, and the objective of the planner is to minimize the total social cost, the sum of costs for all the agents. Then the price of anarchy of pure strategy Nash equilibria would be 5/2. And this is tight. So we'll show now that it can't be, that it's always less than that, less than or equal than that, but there are examples where we actually do achieve such price of anarchy. Okay, so if we have congestion games with linear cost functions, and we look only at pure strategy Nash equilibria, we know they do exist in this model, then the price of anarchy will be 5/2. How do we show that? Say, for simplicity, let's assume, let's just show that for a very simple linear cost function, which is the identity function. Why can we do that? Because the first coefficient AR, we can ignore it by replacing the model with another one where we have just AR identical resources. Okay, that's will be multiplication by AR. And we also can ignore, sometimes not always, we can ignore the second constant BR if we just add BR players that use a particular resource R. Okay, so we can just move from one game, from the original game to another one where the cost function will be of this form. So it would be enough to show it for the identity function. So first, let's show the upper bound. So we have a Nash equilibrium and we have an optimal allocation of the agents. Now, what is the cost to the player? The cost to a player with identity cost function is just the sum of congestion levels on all the resources that the given agent uses. Right? And now we want to bound it with respect to the optimal cost. Right? The optimal cost is given the same way, but with respect to the optimal solution. So we have the total sum of costs for all the agents in the equilibrium. Right? So that would give us the wait, is that me? Up and down. All right. So we have the total sum of costs of Nash equilibrium for all the agents. So each one of them pays exactly the level of congestion on all the resources that they use. So if we look at the total cost which is paid by the agents at each resource, what will it be? The congestion there multiplied by the number of users there, which is just the congestion squared. Right, so this is the same as if we look at all the resources and take the congestion there. Same for the optimal solution. That would be now we want to bound this thing with respect to that solution. Okay. Now we know that for each agent, his cost at the Nash equilibrium, I'd say he goes over all the resources that he uses. This is so if he changes his strategy from SI that he plays to what he would play in the optimal solution, right? Where the rest of agents play according to the Nash equilibrium. This, by the definition of Nash equilibrium, should not be a profitable deviation for him. Right? So what is his cost in this? Okay. So there would be the sum of costs in that at that level over all the resources that he uses in the optimal solution. Right? And now, what are these resources? So some of them he does use in SI. Okay, so from changing his strategy, when he changes his strategy from SI to opt-I, the congestion there does not change. And there also will be some resources here that he didn't use before, so there the congestion will grow by 1. Right? So this is what it is. And this, of course, is less or equal than the sum over the same resources of the congestion that they had in profile S plus 1. Okay? For some of them, this indeed will be the congestion in the new profile. For some of them, it will be less by 1. Okay? But this inequality does hold. Right? And I can't switch this even bound this thing. So if I take the, not left-handed, if I take the sum over all the agents, so what is the total cost? So this is the total cost that the agents pay when the level of congestion on the optimal resources is like that, okay, for all of them. So what is the total level of congestion on each one of the resources? So this is actually, I can just take the summation over all the resources, right? The number of users on each resource there is HR opt, right? And this is what we assume that would there would be. So for now we have this bound. Now one thing that we will do with that we'll have to use some inequality. I'm not going to prove the inequality, but I'm going to just use it directly. Okay. We have two parameters alpha and beta. Beta multiplied by alpha plus 1 is less or equal than that. Okay. Now, this is my alpha, and this is my beta. So now we can write that this thing is less or equal than the sum of squared optimal multiplied by 5/3 plus same thing for alpha squared multiplied by 1/3. Now, this is the optimal value. This is the Nash equilibrium value. Okay, exactly what we have here. Okay, so altogether, if we do the, so we have that the cost of Nash equilibrium will be less or equal than 5/2 the cost of that. So that's the upper bound. We can't go worse than that. How do we show that this actually the best we can achieve? For that, it's enough to just give an example where the price of allocated is 5/2. It's really buffering. Do you see the whole whiteboard at this level, or after the whole thing? So we give the following example. We have Now the strategies for the players are of two forms. So there are two strategies for each agent. Either he plays xi and yi, okay, or he plays xi minus 1, xi plus 1, and yi plus 1. Okay, so there are two choices to make. Now, in the optimal allocation here, all the agents will choose the first strategy. If all of them choose the first strategy, what happens? The congestion, because each one takes the pair with their index, right? So they will be the only user of that resource then. So the congestion will be 1 here and 1 here, and the total cost will be 2. Now there is a Nash equilibrium. It's not a unique Nash equilibrium, but there exists a Nash equilibrium in which all of the agents play the second strategy. All of them do the green thing. What's the congestion of the resources there? So these two resources will be used by I, but also by the neighboring agents, right? So there will be a congestion of 2 here and there. And also, each one of them uses the Y resource with the index plus 1. They will be alone there. So the cost for doing this is 5 for each. Take the ratio. It's 5 over 2. And it's really hard to go without slides. So this was the price of anarchy with linear cost functions of pure strategy Nash equilibrium. If we take into account also mixed strategy Nash equilibrium, what will happen with the price of anarchy? What can happen with the price of anarchy? Can it go down? Price of anarchy, once again, is the value of the worst Nash equilibrium divided by the optimum. Now, pure strategy Nash equilibria are a subset of mixed strategy Nash equilibria. Right? Not necessarily strict subset. There are games where there are only pure strategy Nash equilibria, but in general, that's a subset. So if I take the worst value here divided by the optimum, or if I take the worst value here divided by the optimum, so does the ratio goes down or up? Up, right? So we can, not necessarily, but we may only go worse in a larger set. Okay. And indeed we do. So the price of anarchy for mixed strategy Nash equilibria is the Bolton ratio of 2.618. So it's slightly larger than 2.5 for the mixed case. I want to go into different prices of anarchy and stability for other functions, but do get yourself familiar with the definition and try to train to find prices of anarchy and stability in different games that you know. Okay, where there are 2 by 2 small games, you can just check every Nash equilibrium there and find it in a simple way. Now, besides Nash equilibria being suboptimal, there is also another drawback in them. So by definition, a Nash equilibrium is a stable solution, but it's stable under unilateral deviations by players. So there is no incentive for each one of the players to deviate from his equilibrium strategy if the others are playing what they play in the equilibrium. However, there may be deviations by coalitions. So Nash equilibrium does not cover that. So there might be deviations by coalitions. So to prevent those, we need another solution concept, and that's one named strong equilibrium, because indeed that's a stronger requirement to make. The intuition is a strategy profile is a strong equilibrium if it is immune to inactive deviations by players. Okay. Formally, what it means is that we would say that a coalition of players C has an improving move from a given profile S if there is some collective strategy S prime C. What's that? That's just a vector of strategies for all the players in the C. So there is a deviation of those guys so that each one of them, for each I, is the member of the deviated coalition, his utility from this deviation, so the resultant profile will be S prime C, S minus C, so the rest of the players play according to S is strictly greater than his utility in this. So a coalition would make a move if each member of the coalition gains something from that deviation. Okay? S is a strong equilibrium if no coalition C has an improving move in this. Okay. So instead of having individual players, now we have coalition players. Then the definition essentially as Nash equilibrium. Now, what can we say about the sets of strong equilibrium and Nash equilibrium? So first of all, each strong equilibrium is a Nash equilibrium by definition. Okay, because the requirement is for all coalitions, including singleton coalitions. Right? So every SE is an the other way around, not necessarily true. So there may be Nash equilibria where coalitional deviations are possible. Simple example, prisoner's dilemma. Okay, the unique Nash equilibrium there is not immune to coalitional deviations. The two of the players may move to deny and gain both of them. Would that be a strong equilibrium? No, as well. It's not even a Nash equilibrium, right? Because there we will have unilateral deviations. Okay, so the set of strong equilibria is included in the set of Nash. What? Yeah, I'll take 1 more minute for the last 2 slides. In congestion games, as well, we know we have pure strategy Nash equilibria. We may not have strong equilibria, but if you remember, there was this particular simple subclass of those games called resource selection games, or singleton congestion games, or simple congestion games. Those are congestion games where the agents only choose single resources. Okay? For those games, the set of strong equilibria actually coincides with the set of Nash equilibria. So for those games, every Nash is actually strong. And it can be also found in polynomial time, which is nice. And I wanted to tell you a bit more about condition games. I probably will continue on Tuesday, and we also talk about security games and some computational issues. So see you next week, and your marks for previous semester are on the 8th. You've done well. Don't be worried.